Okay, class. So we have this problem. It has to do with determining if a particular function is continuous at some designated value from a given domain. Okay, so there are three criteria that must be satisfied. Okay, and you're going to find that calculus is filled with these things where you have certain requirements that are necessary in order for a set of rules to kick in. So the first one is that if we're trying to determine if some function is continuous at some x value, you need to make sure that that function, first of all, is defined at that value. So therefore, you have to say the first rule, three rules must all be satisfied. And the first rule is that f of a is defined. So I'm going to call it 1. F of a is defined. In other words, you're not going to get something weird like a 0 in the denominator or something like that. Okay, the second thing is that the limit as x approaches a, okay, of f of x exists. And for these kinds of problems where you have two sides that you're looking at, you'll have to check from the left and the right. And then number 3, you have to make sure that the actual limit that you find is equal to f of a. So therefore, the limit of f of x and this should be a small f, not a large f, of f of x as x approaches a, all right, is equal to the f of a value. All right, so you have those three criteria. So what we do is, the first thing we want to check here is the function defined? Well, let's take a look. Let's take a look at a case where x equals a. I'm sorry, x equals 0. If we're looking at x equals 0, this is relatively going to be a simple one because you'll be using the same function. Why will I be using the same function? Because, ladies and gentlemen, the 0 falls into this range. What I'm talking about here is if you looked at a number line here, right, like this, and let's say that this is 0, right? Here, our key point that we're measuring here is 1. So in other words, when we are at 1 or less, going this way, right, 1 or less, then we're going to be dealing with this first function here, right? If we're going to be greater than 1, in other words, looking at it this way, then we'll be dealing with this function. So since right now we're just looking at 0, we're just going to focus in on this first problem here. So the first part is step 1. Let's go ahead. I'm going to number them to correspond to 1 is this one. Therefore, f of 0 is going to be -2. Why is it -2? Because if I plug in a 0, I just get -2. The second one is, now let's take a look and see if the limit exists at 0. Well, the limit as x approaches 0, we're going to have to look at coming in from the right and coming in from the left. If you're coming in from the right, you're still going to be in here. Let me change the colors here to show you what I mean. Make this red. You're still going to be coming in here. You're coming in from the right. So you're coming in this way, and we're still going to be dealing with that same function. What function? I'm talking about the x squared minus 2. And when you come in from the left, you're going to be looking at the same thing. And the rule for limits say that as it approaches and it becomes an incredibly smaller and smaller value, for example, this might become -0.00000001, something like that, and this becomes +0.00001, it's so minusculely small that you essentially just assign it to 0. And on both sides, it's as if though you had a 0 there. So therefore, this is going to be -2 as well. And the limit as x approaches 0 from the left is also equal to -2. And therefore, the third criteria is the limit of f of x as x approaches a equal to f of a. The limit as x approaches 0, right, of f of x equals -2, and, right, f of 0 equal -2. Therefore, step 3 is satisfied. So 3 is satisfied, 2 is satisfied, 1 is satisfied. We say that at x equals 0, f of x is continuous. Okay. All right, so we're going to repeat that process for x equal 1 and x equal 2. So let's see that. Okay, so now let's take a look at x equal 1. Okay, the first criteria, right? F of 1. Since 1 is equal here, this is the one that we're going to use to establish the criteria, and it does exist there. Therefore, at 1, the value you're going to have is -1. 1 squared minus 2 is -1. The second one now we need to look at is, let's establish the limit as x approaches 1 from the right, of f of x. Let's take a look at that. If you're coming in from the right, here's my number line, right? Part of a graphing system here. And here is 1. If I'm coming in from the right, this is where x is, you're approaching 1 from the right, you're going to be on the right side of the domain, which means you're going to be looking at this. Therefore, you'll be looking at this equation here, right? And therefore, the best that you can hope for, since it cannot be equal to 1, you know, when it's actually going to be a 1, that would put this at about a 1, but it's going to be like a circle right here, like an open amount. And then your function is going to be going, as you go further to the right, right? Say this becomes a 2, you're here at 2, this comes down to a 0, and your function is going to look something like this, right? Okay, so as the x approaches 1 from the right, okay, you're going to get, let's give it that value, as you get close and close enough, by rules of limits, you're going to assign the value to it of 1, because you're coming in from the right. So you're going to use this equation here, right? So you're going to have 1 plus -1 plus 2 is 1. And then when you come from the left, you're going to be using this function here, right? But this function is a little bit different, because now you're going to be on the left side of the 1, including the 1, right? In fact, when you actually are at 1, you're going to be at -1. You're going to be down here, right? -1. You notice that when you plug in a 1 in here, you're at -1. So the limit of f of x equals -1 as x approaches from the left. So therefore, step 2 fails already, and therefore this limit does not exist. So the limit as x approaches 1 of f of x does not exist, dne, right? So just by that, it's not continuous. And therefore, of course, f of a is not equal to the limit as x approaches a of f of x, right? It can't be. So therefore, we say at x equal 1, right, f of x is not continuous. And before you jump, always double check your very simple substitutions. So let me see, make sure I did this right. If I came in from the right, I'm using this equation. I plug in a 1 in here. And when I plug in a 1, what I get is a 1 is my answer. And that's what I got here. And when I come in from the left, comma, and when I come in from the left, right, you're coming in this way on your number line, this way, you're going to be all the way down here. So therefore, you can see that these two are two completely different points here, right? In fact, this looks like to me like it's a parabola, right? That's what it looks like to me. So it's going to be a parabola, probably like this. And, you know, obviously it's not a continuous function because as you're analyzing the domain coming to on this side, you're going to have a -1. So this one should be -1 here. There you go. And therefore, in order for the limit to exist, this limit, the right-sided limit and the left-sided limit have to be the same value. So let's review the steps, and I'll do it in pink. You define, make sure that the function is defined. That's your first step, right? Second step is that you're going to check the limit. But in order for you to check the limit, you have to do as you approach from the left and you approach from the right. Sometimes if you have conditionals, like we do here, right, it shows that it is not continuous. Like in this case, as we come in from the right, we will be using this function, right? And by using that function, when we substitute, we get a 1 as the limit for that. But as if we were coming in from the left, you would be using this function, right? Which then gives us a -1. And therefore, because these two are not the same, the limit does not exist. And because the limit does not exist, then the function cannot be continuous. Okay? So that is, so part for x equal 1, we say it is not continuous. Now let's take a look at x equal 2. Okay, at x equals 2, let's take a look at that. All right. All right. So the question is the function, is f of x continuous? At x equal 2. So in calculus, when we say continuous, it's not the same thing as just saying, oh, I plug in a value and there's a number there, it means it exists. No, what you're doing is you're analyzing throughout the life of that function, and that life of the function with respect to the domain that's given. And continuous, we're talking about smoothwise continuity all the way through. Okay, and if you don't have that, then you cannot claim continuous. Okay, and we have 3 tests that we do for that. First of all, that function has to exist there, right? That's the first one. Secondly is there a limit there? Because definition of limits is something that we permit ourselves to do in calculus, that we say for incredibly very, very large or very, very small numbers, that they impact in a way so that we allow the values to say that there is a limit, not necessarily equal, but a limit. And if we do have a limit there, you know, one way to think about it is that it's so close to each other that almost it's like a spark jumping over a little gap, that it's so small that it's, you might as well be together. Okay, if it goes back to the whole idea of what a line is comprised of. If you take 2 points like this and then you start subdividing those points, right? Like so, like that, and you just keep doing point. At some point, you would need a super duper magnifying glass, and if you took a line like this and took a magnifying glass to a little piece of that, you would find that that thing is probably made up of points like this, that you can find that difference in there. Okay, so anyway, so moving on back to this. So the first step is item number 1. If you assigned a 2, if we were going to do 2, we'd be using this one because we're going to be on the right side. Again, looking at the function, right? Here is 1, here is 2. If we want to evaluate the function at 2, on the right side of 1, we're using negative x plus 2. So at 2, you're going to be at 0, right? And at 1, you're going to be at 1, right? And that's as far as you're allowed to go. And 1 was going to have an open line like this. And then this function goes like this, right? Like that. So we're going to be analyzing, looks like, since we're looking at 2, we're going to be analyzing going this way and going this way for continuity, right? Which means we'll be dealing exclusively with this function. Okay, so let's take a look, because that's all we want to know. Is it continuous at this point, right? All right, so let's take a look. First of all, f of 2. F of 2 equals, okay, negative 2 plus 2 equals 0. All right, that works. Item number 2, let's take a look at the limits, right? The limit as x approaches 2 from the right of negative x plus 2 is equal to what? Well, if you're approaching from the right, you're coming to the 2, you're getting close to 0. And the limit as x approaches 2 from the left is the same thing of negative x plus 2, is you're coming this way, right? Which you're approaching 2. So therefore, this also becomes 0. Let me fix this because that looks like a 6. 0. Okay. All right. For some reason, doesn't want my zeros to come out nice. Let me see here. Okay, come on. Okay. So therefore, step 1 is passed. These two are equal. That passes. Now the third step is this equal to this? Well, we know that the limit as x approaches 2 of f of x is equal to 0. And we know that f of 2 is equal to 0. Therefore, step 3 is also met, right? Because these two are equal. So therefore, the limit, f of x is continuous at x equal 2. So we had 2 that were continuous, that was at 0 and at 2, and then 1 that was not continuous, and that was at 1. And that's pretty much it.